What is up, guys? I'm back here with another video, and today I'm going to talk about the Gaussian Naive Bayes machine learning model and how it works and all of that. So Gaussian Naive Bayes, what it is it's a model that can make prediction classification or classification predictions. So for example, in this data set, we have patients with cancer and without cancer. A Gaussian Naive Bayes model can predict whether or not someone has cancer, given the data set. So the first thing that we do, and all this code, now this is, I'm going to explain how this model works exactly. And all of this code, don't worry, you won't have to write all of this. This is just me showing kind of how it works under the hood. The actual code to use this model, I've left in the description below. But anyway, we start off by splitting out the data set between people that have cancer and people that do not have cancer, right? And we have two features for this data set, just to keep things really simple. We have the radius and the perimeter for each for the tumors, right? So we look at the distribution of the radius for the group that has cancer. We look at the distribution of the perimeter for the group that has cancer. And we do the same thing for people that do not have cancer. And first of all, we calculate what percentage of the whole data set as a whole has cancer and what does not. We get that 62% of the data set has cancer and 38% does not. So knowing nothing about an individual data point or patient, or I guess these are patients, knowing nothing about an individual patient, we can assume that there's a 62% chance that they have cancer. And there's a 38% chance that they do not have cancer. So let's take an individual data point. Let's make this up, and let's say that their mean radius is 15 and their mean perimeter is 110. So we're going to approximate the likelihood that they do have cancer using Gaussian naive Bayes. So the way this thing works is it's basically probability of C. And what I represent this C prime, this is just an individual data point. So probability that the individual data point has cancer or has the condition, whatever it is, the probability that they have cancer is equal to the probability that they have cancer just given the data set as a whole, multiply times the probability that the data point has, a certain value. In this case, it would be the radius given that they have cancer. So probability of the radius being 15 given that they have cancer, probability of the perimeter being 110 given that they have cancer, and then so on for situations where we have more features, which most situations will, of course. So we start off with this predicting that they have cancer. We start off with a base of 0.62, and the reason for that is because knowing nothing about the data, 62% of the data has cancer, so we can assume there's a 62% probability that they have cancer. But we're going to take into account their radius, and we're going to take into account their perimeter. So if we look at radius, and we're going to, I'm going to show you here in a minute. So we're going to, so what's it going to look like is we're going to look at 0.25, or I'm sorry, 15. This is their value for their, and they seem to stop about here. And if we look, that's about 0.25, right? And now what happens, ignore the line, when we go down, we have 0.25. And now we're going to multiply that by 0.04 because, let's go here. So they have, here they have a perimeter. If we have a perimeter of 110, it doesn't take much for us to realize. Let me draw another line here. And we got about 110 probability, and we're still at 0.04. So that's actually not too bad. So, well, it's not that it would be bad. There's anything that is bad, but now we multiply that by 0.04, as you can see over here. And when we multiply these up, we get this value here. So that is our likelihood that the patient does actually, in fact, have cancer. So for the probability that they do not have cancer, we repeat the same process. So we start off with 0.38 because, like I said right off the bat, we can assume that, if it fits the rest of the data, there's a 38% probability that there's no cancer. But then we look at these values here. So we look at the mean radius of 15 once again. And if you look, 15, it matches up to be around 0.3. And then if we look over here at 110, I guess 110 would be right over there. We get about a 0.04. So if you look at it, or 0.0, that's wrong. Okay. But yeah, we get a 0.08% probability that they have a perimeter of 110, given that they don't have cancer. When we multiply these up, we get a 0.0091, which is slightly higher, which means that we actually, in fact, predict that this person does not have cancer for the situation. So basically, just to reiterate, this is probability that any patient has cancer, probability that a patient has cancer, or I'm sorry, probability that a patient has a radius of 15, given that they have cancer, probability that a patient has a perimeter of 110, given that they have cancer, all multiplied up. Here we have probability that any patient does not have cancer, multiplied by the probability that a patient has a radius of 15, given that they don't have cancer, multiplied by probability that a patient has a perimeter of 110, given that they don't have cancer, all adding up to this value right here, which is a little bit higher. So in this situation, we predict that they do not have cancer. And some situations where you want to use this is you want to use this in situations where the features are continuous, which means you have data that is essentially numerical. The features are numerical. We have things like perimeter, radius in this situation, things like weight, height, revenue, anything that's numerical. We want to, because that's when these Gaussian distributions work. They work for data that is continuous. They don't work for data that is categorical. So if you have categorical data, you want to use the multinomial naive Bayes instead. Okay. Secondly, another good thing about this, another time you want to use this, is you want a model that is really quick. You don't have all day to hyper tune your model and try all these different combinations to come up with the best model. You want a really simple model. This is a good one to do because there's only one of these hyperparameters, which essentially means generally the model that you just start off with is most likely going to be the best model, and they compute really fast. They're very fast models. And also you want a model that is very explainable, because this, if you want one, if you're going to have to explain the results of your model to someone, that's especially someone that doesn't really understand this technology stuff very well, you're going to want something that is very easy to explain. In fact, I've heard of a lot of data scientists where they actually, in their company, they may find that the best model might be a random forest, and then they'll actually use that model and they'll put that model into production. But then they'll use a more simple model like this, or maybe a logistic regression or something, just so that they can explain to people at their company outside of tech that how everything's working. Just an interesting little thing I thought I'd share there. But anyway, that has been the video. So I hope you enjoy the video, and my next video will be quite interesting. I really hope you enjoy. Bye.